Alrighty, hello everyone, and welcome to our webinar today. I'm Patrick O'Brien, and we'll be taking a look at how to apply inherently safer design techniques to cybersecurity. And so we've seen that inherently safer design and the hierarchy of controls is something that's been used for a long time in process safety and other safety areas as well. And thinking about if we can, lower the amount of inventory we have of a hazardous chemical or lower the pressure or temperature at which it's stored, even in the event that we have some sort of release, some loss of containment, we're going to have a lower consequence of that event because we have, less risk, less of that hazardous component. And so what we're going to do in this webinar is really take that idea and think about how we can apply that in a cybersecurity mindset. And we'll see that there are several, common cybersecurity best practices and techniques that are really an offshoot or are similar to this inherently safer design principles. We'll look at, secure by design and thinking about how cybersecurity aspects can be built into a component while it's developed as opposed to being added in at the end. We'll also take a quick look at cyber-informed engineering to think about how by looking at certain high consequence events and having non-cyber related mitigations or fail-safes in place, we can limit the potential impact that a cyber event can have. And so that will really guide us through our topic today. We will be using the GoToWebinar application for this. And so you do have the opportunity to ask questions throughout the presentation. And based on the earlier session, we should have around 10 to 15 minutes for questions at the end to go through those. And so before jumping into the details of the webinar, I like to just give a brief introduction on myself. So as I said, I'm Patrick O'Brien. I am the Assistant Director of Engineering for Exida. And so I have my background in chemical engineering. I really started out more on the process and functional safety side, everything from hazard and operability studies through LOPA, still verification, all the way to proof test development and the operations and maintenance phase. And so I have a lot of background on the safety side, but probably 5 or 6 years ago, really started to dig into the cybersecurity aspects as well, as we saw that the potential to compromise safety instrumented systems and control networks, not only had major operability concerns, but also potential safety concerns as well. So now I support both of those areas and get to work with a lot of different sites on those aspects. And as part of getting involved on the cybersecurity side, I was able to work as one of the authors for exida cybersecurity book, implementing IEC 62443, a pragmatic approach, as well as help lead the project for the CCPS concept book, managing cybersecurity in the process industry. And so with that background, I always like to take, process safety and functional safety techniques and think about how we can apply them to cyber as well. Now, before jumping into the details of today's webinar, I also like to provide a brief introduction on Exida for those who may not be familiar. And so at Exida, we work with our customers to achieve safe, reliable, and secure solutions. And we have 3 main ways in which we do that. The first is our enterprise tools. So we have a series of software tools in the Excellentia platform that help customers to complete functional safety lifecycle tasks, complete alarm rationalization, and also do cybersecurity risk assessments. We also have a series of tools in the OEMX platform to help manufacturers do studies like failure modes and effects analysis or failure modes, effects, and diagnostic analysis, as well as some threat modeling using the ArcX tool. And so really the idea with these tools is to help provide a more efficient way to go through and complete those necessary activities for the safety and security life cycles. Next, we have our certification and assessment group. And here we can provide functional safety certification to the IEC 61508 standard, as well as machine safety certifications to IEC 62061 and ISO 13849. We're also a notified body through our Irish office for some machinery certifications. And then in addition to the safety side, we can provide automotive certifications for safety and cybersecurity, as well as cybersecurity certifications to the 62443 standard. And we'll see how those standards cover some aspects of inherently safer design techniques a little bit later in this presentation. And then lastly, for our lifecycle services group, here we work directly with the operating plants, with the asset owners, to help them do functional safety, alarm management, and lifecycle tasks. So working directly with the company to do a cyber risk assessment or analyze the potential impacts that a cyber event could have for their site. And what's really nice about being able to work with all of these different groups is you really get to touch each of the stakeholders in the industrial space, everyone from the product or component manufacturers to the system integrators that put those together, and then the asset owners that will operate these sites. And so with that, we're able to see how cybersecurity and safety touches each one of those aspects. And in today's webinar, when we look at using these inherently safer design techniques, we'll see that they don't just apply to one group in the cybersecurity supply chain. Really, there are techniques and strategies that can be taken and applied to the component level, system level, and even the site and organization level. And so in our webinar today, what we'll look to do is start by going back to the inherently safer design techniques, understanding the history of how this was developed and the core concepts that govern this for use in process safety. From there, we'll go on to look at how we can apply these techniques to secured by design and building more inherently secure components and systems. And then lastly, we'll look at how we can grow on those techniques to then assess opportunities for an inherently more secure, more robust design at a site and even an organization level. So to get started, we'll root ourselves in the process safety fundamentals for inherently safer design. And really, inherently safer design, it is a process safety strategy, but it's a framework for understanding kind of basic human thought processes and things that we've been doing for as long as we've had records. And the example that people always like to go back to and think about is picturing a settlement on the side of the river and thinking about where is it safest to build a house there. The reality is, if you're too close to a river in an area with flooding, those houses are going to be the first to be impacted. And so you want to make sure that the houses are set far enough back or high enough elevation so that if there is a flooding event, that house is going to be protected from it. And so if we just think about this picture, if this was a flooding area, those houses that are set higher up on the mountainside are going to, naturally, by the position that they're set in, experience less damage, less of a negative impact from that flood. And so the idea of picking the safer location or something that is inherently going to have a smaller consequence really is consistent across time. When we think about applying this in the process safety context, in the late 70s and early 80s, Professor Trevor Kless really started to take this idea and mold what we think about today when we talk about inherent safety in the process industry. And really, again, that idea is, what can we do in the realm of an operating plant to limit the potential for a negative consequence? So yes, we may have to use a flammable material, but if we can use a smaller volume of that material, or if we can use a lower concentration of an acidic material, even if there is a release, we're going to have a lower consequence event compared to if we had very high volumes, very high concentration. And so oftentimes the way that these ideas for inherent safety are applied is through the use of the hierarchy of controls. And this is really part of how we can build inherent safety into our lifecycle techniques and our strategies. And so the first step is we have to identify, assess, and understand our hazards. So if we don't understand what the hazards are properly, we're not going to be able to pick the right techniques or implement the right strategies to try to limit those hazards. And so everything starts with an understanding of our baseline risk and what can go wrong in our system or in our site. Once we have that understanding, then we can look at applying inherent safety principles. These are things like substitution, simplification, moderation, minimization. So what can we do to limit the potential for a hazard, minimizing volumes, using a less reactive or less explosive material? So we want to think about everything that we could do to limit that consequence if we did have a release or loss of containment event. Once we've exhausted what we can do to limit that consequence, then we can look at adding engineered layers of protection. These would be things like, pressure relief valves, having dike funds or containment areas, looking at implementing a safety instrumented system to reduce the likelihood of a loss of containment. When we can't add, further IPLs or engineered protection layers, then we could look at falling back to administrative controls. Can we improve operating procedures to reduce the likelihood of an error leading to a potential event? Can we improve visibility, improve awareness through administrative controls? And then once we've done everything we can, then we look at where a residual risk falls and see, do we need to take further actions or not? And the key here is that as we go through these steps, our controls become less effective. So something that we can do to inherently limit the consequence of event is really going to be the most effective control for addressing that risk. Then engineered protection layers are less effective than that, but more effective than administrative controls, which again have the least impact overall on our likelihood. And so if we focus in on this second step here for applying inherently safer design techniques, there are kind of four fundamental concepts that we can look at. And here we have just a simple example from the safety side. And this is actually, each of these are examples I've seen from working with several different sites. So just simplify to be able to talk through a concept. So the first one, substitution. The idea here is to replace, one component or one unit with something that has a lower consequence severity. In this specific manufacturing example, there is a specific adhesive type that had to be used, and the nature of that adhesive was that it was quite toxic. But the site had a choice between using a liquid format of that adhesive or an aerosol version of that adhesive. And they were comparing the processes. The aerosol version worked a little bit better, it ran smoother, it was maybe slightly more efficient. But when they looked at the comparison of what would go wrong if there's a loss of containment, if you had a leak of the liquid version, it was in a contained area, so it would have limited spread. And unless someone was right in the area where that leak occurred, there was a very relatively low likelihood of having a serious injury or worse from that loss of containment event. Similarly, if there was a loss of containment of the aerosol version of that material, it would quickly spread. It wouldn't be contained within a certain area, and there was a much higher potential for a severe safety impact. And so with that in mind, comparing both options, the site made the decision to go with the liquid format because that was going to have a much lower consequence if there is a release. On the simplification side, a common one that we see is improving HMI graphics and improving the amount of alarms that go to operators to avoid alarm floods by going through that rationalization process. And we've seen over time that the design guidelines for HMI graphics have moved away from having many colors and flashing lights to using more of a grayscale, providing the key information on that page for the operators to see everything coming into and going out of a unit. And through that, we've simplified their view of the process. We've made it easier for them to make informed decisions and lowered the likelihood for a negative impact. Similarly, by going through alarm rationalization and ensuring that only the alarms that operators really need to see come through, they're going to have a better chance to respond to the correct inputs and be able to limit the impact if a disruption occurs. For moderation, here we could think about the process parameters that we are using for a reactor. And by lowering the temperature and the pressure that the reactor is operating at, we're going to have more room between our normal operating conditions and our maximum allowable working pressure, maximum allowable temperature, so that if we do have a slight disruption or some sort of issue, we're further away from that loss of containment or that potential consequence event. And so by, again, making a conscious decision to operate at a lower temperature or pressure, we have, more bandwidth if there was some sort of small leak, because it's at that lower pressure or lower temperature, it's going to be a less severe impact than if it was at an extremely high temperature or pressure. And sometimes this will go into the decision-making factors when picking one technology or one approach versus another for how to complete a chemical process. The flip side of moderation and kind of something that we often see that is moving away from an inherently safer design is drift of normal operating procedures and normal operating conditions. And we have seen cases where the instructions are to operate something at relatively low temperature or pressure, but over time, operators become used to running that at higher pressures, higher temperatures, and they drift further and further away from those normal set points. And we can see there, as your space between where you're operating and the significant event gets smaller, you're operating from a riskier position. Then the last one on the minimization side. So for a number of processes to get the volume of nitrogen required, it's sometimes necessary to use liquid nitrogen lines as opposed to gaseous nitrogen. But if there is a leak of that liquid nitrogen, it will create a higher flow or higher accumulation of nitrogen compared to a gaseous line. And so because of that, companies are very thoughtful of where liquid nitrogen lines are in place. And we have seen some examples where there was legacy equipment that no longer used the liquid nitrogen lines. And so those lines really needed to be pulled out to lower the risk of the leak. And so in this case, by minimizing the inside piping runs of liquid nitrogen, there were fewer scenarios where there could be a major leak event. So these are a couple of examples to really kind of ground us in how inherently safer design techniques can be applied in different processes. It's important to note that this is not just a best practice that some sites look at, but actually in the latest updates to the EPA Risk Management Program, or RMP, they are specifically requiring a type of inherently safer design analysis that's called Safer Technologies and Alternative Analysis. And this is required for chemical, petroleum, and coal product manufacturing facilities. And it really forces them to go through and follow the hierarchy of controls. So looking at, is there an inherently safer design measure that could be implemented? Could they pick a less volatile set of reactants? Could they use a reaction process that's at a lower temperature or pressure? Is there some safer alternative out there? Did they really pick the safest option for operating that site? And then where that's not feasible, then dropping down to passive measures like a dike or a bund, active measures like PSVs and SISs, so looking at those engineered protection layers, and then finally implementing procedural measures such as the operator procedures and training. So really, we can see that it's not just a best practice, but actually required by regulatory enforcement to think about things from this hierarchy of controls, inherently safer design approach. And when we look at taking that and applying it to cybersecurity, it's not just a one-to-one mapping where we can think about it at the site level, but it actually fits for different layers, different pieces of the overall cybersecurity framework. So from a component perspective, so looking at a single hardware or software component, really the secure by design concept ties in nicely with inherently safer techniques. At the system level, we could talk about secure by implementation or secure by integration. So when those components are put together into a system, there are configuration decisions to be made. There are choices about how the system is going to work. And there are opportunities to really limit the inherent risk of that system based on how it's implemented. As we get up to the site level, now we have more information about choosing physical security measures and personnel security measures. We also have the ability to choose between using an SIS or a computer-based protection for a safety scenario, or implementing a mechanical protection that is separate, totally disconnected from the network. So we can make decisions on those compensating measures. And then lastly, we'll take a step back and think about how the concepts of inherent safety can even be applied at the organization level by thinking about what steps an organization can take to be more resilient to cybersecurity events and limit the overall negative impact on the organization if they were to experience an event. And so to start, we'll apply these techniques at the component and system level, and then we'll build from there to the higher levels. So if we start by components and use secure by design, our core principle here is that security measures are going to be most effective when they're being built into a component instead of being bolted on at the end. If we can build something from the ground up using a secure set of software, we're going to be in much better shape than if we are trying to add antivirus or whitelisting onto a legacy Windows 95 device that we can't update, can't patch, can't address any issues on that component. So instead of bolting it on at the end, we want to look at building it into the component throughout the life cycle. And some key steps to be able to do this involve including security as part of the development lifecycle. So again, each step of our V model or our agile development, we really want to have security as a step, each part along the way. Next, we can look at minimizing the attack surface for the component or the aspects that could potentially be leveraged by an attacker. And then lastly, we want to design for defense in depth. So if we start by looking at the secure development lifecycle, here we have an example of building it onto a typical V model, but we can apply this to an agile development lifecycle as well. But really what we need to do is at each step in the development lifecycle, we need to build in the security elements of that step. So we're not adding security in at the end, but we're actually defining our security requirements up front, building security into the architecture design for the component, assessing potential security risks, and really going along each step of the way, doing our specific security testing to prove that we've implemented the right controls. And really, the standard that we're seeing define the guidelines for implementing a secure development lifecycle in the industrial space is the IEC 62443 standard, and specifically Part 4-1 is all about a secure development lifecycle. And in the practice areas for that standard, there's a specific security practice called secure by design. So really that idea of secure by design is built into the development lifecycle in that standard, and is really a good way for manufacturers to build security into their process as they develop their components. In addition to including security as part of the development lifecycle, there are also important steps that need to be taken to minimize the attack surface. And we can think about this from a hardware standpoint. So looking at a controller as an example of an embedded device or a component, thinking about, well, what interfaces are available that someone could use to connect to that device. And so for each of those interfaces, what is its intended function? If you have one interface for a service connection, that will have higher levels of access than, say, one interface that's just used to provide information to an HMI. So we want to limit exactly what you can access from each interface to the minimum amount required for its function. Additionally, we can think about, well, what permissions are required to access those different types of interfaces, and how do we make sure that the security capabilities for that interface match its use. On the software side, we can think about applying those same techniques to the actual code running on the component. Reducing the amount of code that executes by default is going to reduce the amount of code that could be readily exploited. Restricting access to the code, again, to the minimum amount of people who should be able to modify it. Reducing the privilege at which the code runs, so it would have less of an impact if it's corrupted. Clearly identifying all of our software components. So just like we have to understand what our interfaces are to secure them, if we don't understand what's running as part of our software, we're not going to be able to accurately harden it or remove the aspects that we don't need. And again, it may sound really basic to remove unused software components, but the amount of components that we've looked at that have massive libraries that are not used at all or only very slightly used in the application, it's surprising how many times it's the simple things that aren't being fully addressed. So absolutely, simplifying the code, running only the minimum amount that you need can definitely help to improve the design and the development of the software. And we can also apply that on the feature side. So again, if a feature or sub-feature is not readily used by the vast majority of users, it could be disabled by default so that those users who really do need it will be able to always go and enable it themselves. And then the last one that I always like to talk about is risky features with limited benefit. Asking the question, do we really need this feature? And again, it sounds basic. People would ask, well, why would you have a risky feature that doesn't have much of a user benefit in the first place? But the reality is probably because one customer asked for it. Think about how many of the control systems and controllers out there today have pathways for easy remote access. There may have been a time where that was really desired for ease of troubleshooting and making adjustments. But as we understand the security implications today, do we still really want that access to be present? And if it's still included, do we want it to be enabled by default, or should it be disabled? Another thing to think about for the manufacturers as they make these decisions is, what is the security context of the component? Because depending on the context, different decisions may be appropriate. For IIoT devices that are going to be, often not through physical, security perimeters that could be more readily accessible, they may have to have, different provisions for preventing physical manipulation than a controller that's designed to be in a locked cabinet in a locked site perimeter. So by understanding that context, we can make decisions about what security controls really need to be in place. Another core concept of the secure by design approach is defense in depth as part of the security lifecycle. So assuming that earlier layers of the defenses may fail, and having multiple independent mechanisms in place to limit the likelihood that that component is compromised. And really, we could think about identifying those barriers and those different security mechanisms throughout the life cycle in which the product is developed. And if we think about IEC 62443-4-1 as the standard guiding our development lifecycle. 4-2 is then the standard that defines the specific security capabilities to help implement that defense in-depth approach and have multiple protections in place to limit the likelihood for unauthorized access to a device through user access control, limit the probability of the data or the system integrity being compromised, and limit data flows and connections to the devices. So really using these different security requirements along with the secure development lifecycle, it's possible to build in much higher levels of security upfront into components so that then when using those to build out a system or an overall site architecture, you can have a much more secure starting point for those building blocks. And so here's just an example of one of the foundational requirements in 4-2, looking at how at higher security levels, more and more capabilities can be built into the product to protect against unauthorized user access. And so if we think about summarizing the secure by design techniques and applying them to the ISD principles, for substitution, we could think about replacing legacy or vulnerable software components or databases with more technically current versions and stripping out those parts that are going to hold our overall security back, replacing them with something that has basically a lower risk of inclusion. For simplification, creating simple enough software, further reducing complexity can help us limit the potential for errors, limit the amount of code that's running that can be exploited, and that's going to help lower the attack surface for the component. For moderation, for the features or the interfaces that do require access, can we limit which accounts are able to use that feature? And again, if a feature has a potential for a major impact on the device, is it something that all account types should be able to access or only administrator accounts? And then for minimization, we can think about minimizing interfaces to the device. So again, limiting how many potential entry points there are, minimizing shared resources if we have multiple compartmentalized functions within the device. How much do they need to talk to each other or share resources? And again, by minimizing that overlap, minimizing those interfaces, we can make a more robust component. And so that guides us through opportunities to make a single component more secure, but we can certainly build from there. And if we think about building a secure system, so just picking components that have security capabilities isn't enough, because if we install them into a system and we don't configure those capabilities, we don't take advantage of them to their fullest, that system as a whole is not going to be robust, not going to be resilient to cyber events. And again, depending on the context in which it's used, how we're implementing that system, the same component could have very different risks if it's used in a low criticality, let's say monitoring application versus a critical control application or a critical safety application. So we have to understand how that component is going to be used within the system to understand the right way to treat it. We can also look at the key steps that system integrators need to take in order to help achieve security overall, and think about how we can still build off of those inherently safer design techniques and apply them at the system level. So if we think about moving from the attack surface of a component and then evaluating attack surface overall for a system, we start to introduce more layers of attack surfaces. In addition to the hardware and software aspects for each component, we also have network aspects. So how many devices are connected on the network? How many interfaces are we allowing into that system? Do we need to allow remote access to it? Do we need to allow it to access every other system on our site network, or should we really be limiting that traffic? We can look at the social engineering aspects. So how many user accounts are we developing? And are we following least privilege and making sure that operator accounts can only view and change set points, that a limited number of engineering accounts are in place and that those are required to make configuration changes. Are we separating control and safety accounts? So there are a lot of things that we can do from the social engineering side to really limit our risk if an account is compromised. Concepts like separation of privileges or dual approval, again, we can also limit how much a single account can impact the system. And then again, building up from software and hardware components with limited attack surface, just like we want to limit, let's say, the code that's executing within a specific application. If we look at our engineering or operator workstations in the industrial environment, there's an extremely limited amount of software that should be installed on those computers. Yet time and time again, when we go to sites and we evaluate and gather what's there, we're seeing internet browsers, we're seeing user-to-user messages, games, lots of bloatware, so things that just don't need to be there, and provide more of a foothold that attackers could use to find exploits and compromise the system. Legacy or no longer needed remote access software, that's another big red flag that we've seen time and time again. So really thinking about how we can go through hardening and pull as much of that attack surface off as possible. Additionally, the defense in depth concept is still very relevant at the system level. We can think about building multiple layers of security defense into that system so that each layer provides additional mechanisms. So, for example, not just relying on a single password, but if we are going to allow remote access requiring multiple steps with a jump host and multi-factor authentication, looking from the network segmentation side, establishing a DMZ either with one firewall or two firewalls so that we don't have a high-risk enterprise network connected directly to a critical control network. So we can really take that concept of defense in depth and expand it out to the overall system. And again, if we build on that single controller and think about practical application of these techniques to the system, it's all about minimizing traffic across trust boundaries, so limiting access to the zones, limiting remote access unless it's absolutely needed, using least privilege for all of our human interfaces, taking advantage of the security capabilities within the devices in our system. If we do have legacy devices, being aware of that and compensating where we can, and really building in defense in depth for multiple protection mechanisms to protect against different threat scenarios. And so then as we take these concepts, we can continue to expand them out to the site and even the organizational level. So our next level up, a site consists of oftentimes multiple different systems, multiple package units. So we could have lots of different security zones that are all part of one IICS site. We have choices about how we're going to separate or integrate safety and control functions. Do we have a single integrated system? Do we have a separate control network and a separate safety network? These are decisions that will be made by the asset owner at the site level. We can also have better control over physical security and access control, better control over our HR processes and how we manage personnel security. We can make decisions about non-hackable alternatives. So are we going to use a safety instrumented function for protection? Are we going to use a mechanical pressure relief valve? Or in some cases, could we use a hardwired relay that's not connected on the network if we have an event that is truly so extreme from a cyber side that we need to limit the impact if it were to happen. And so there are multiple different techniques for analyzing risk at the site level and pick the right measures to apply. In the IEC 62443 standard, part 3-2 really goes through a detailed approach for security risk assessment and how to best analyze and understand the risks associated with sites and systems. Cyber-informed engineering developed by Idaho National Labs is another way to really look at and understand the worst case impact of cyber events and what steps need to be taken. And so here we can look at building out from, again, first our component to our system. Now we could have our overall site with multiple separate systems. In this example, we have a separate control and safety zone, as well as a few other simple devices. But these are the types of decisions that we can influence at the site level to affect our cybersecurity inherent posture. And so what I want to do here is just take an example from consequence-driven cyber-informed engineering as an example of how we can apply these inherently safer design techniques. So some key assumptions here are that any and every industrial automation system is vulnerable to compromise, that critical systems are increasingly being targeted by aggressive and sophisticated threat agents. And again, if we think about the amount of events that we're seeing, these are some very reasonable assumptions to make, and that with enough time, a sophisticated attacker can and will compromise any systems. And it's not possible to have any cyber protections that eliminate the possibility of compromise. And so with that in mind, CIE goes through 4 different phases. So the first phase, looking at consequence prioritization. So what are the systems that absolutely cannot fail? What are our high consequence events and that are really coming out ahead of the rest and saying this is our worst case scenario? Phase 2, understanding information about all of the systems. What access points are there? What devices could potentially lead to that worst case outcome? Looking at the kill chain analysis to understand what devices or targets need to be compromised by an attacker in order to get to that worst case outcome. And then lastly, mitigation. Once we understand the way in which that severe event develops, where are the different places that we can address it? And if we think about mapping CIE onto these inherent safety concepts, phases 1 to 3 about understanding the those critical systems and the consequence they have through understanding the way in which the attack develops is really our first step here. Identify, assess, and understand the hazard. So what are the events? And then from a mitigation standpoint, the first approach in CIE is to say, can we reduce this consequence of a cyber event by removing connectivity to a critical system? And so for certain systems, if we look at a national level for critical infrastructure, if there is a single component that could cause a nationwide power grid failure, we might look at that and say, well, regardless of how well protected that component is, the fact that we have a single point of failure for the entire network is unacceptable. So there's nothing that we can do from a protection standpoint. The only way to mitigate that risk is to implement a different design for the system that's more segregated, so there's not that single point of failure, and to entirely remove that possibility of that connection from the system. If that's not practical, we could look at implementing mechanical protections. So let's say we have a very high consequence loss of containment event or overflow event. If we have a mechanical non-cyber related protection that we can put in place to relieve the pressure, contain the release, that's going to help to significantly reduce our potential consequence from a cyber event. And then where not possible, can we use other methods to recover more effectively from a potential event? So if we have a control system failure, can we fall back to manual operation? And we've seen this in a number of attacks, like the earlier Ukrainian power grid attacks, where because the site operators still understood how to work the site manually, even though the control system was down, they are able to respond much more quickly compared to a site that required the automation systems to run. So even at the administrative controls levels, there may be things that we can do to become more resilient from attack. And if we take this concept of kind of CIE and inherently secure design techniques, we can actually even expand out beyond looking at a single site and think about how an organization as a whole could operate with this in its mindset. And on the process safety side, there are certain organizations who don't want to operate certain chemical processes because the risk of a loss of containment event is so high that instead of investing in that industry, they're going to substitute that and invest in another industry that they see as having a lower risk. And so when we think about mergers and acquisitions and changing risk profiles, there are some organizations who are really mature at evaluating this at the organization level, as opposed to a site or system level. One thing that we could think about is, substitution. So substituting something that is extremely reliant on automation to more of a manual backup, or having options where it could run automatically in some cases, but you have a manual failsafe to fall back on. We can even think about it on how an organization rolls out their cybersecurity procedures. Having simplified procedures that are easier to understand, written in a way that the actual operation personnel and site personnel can use them, those organizations are going to be much more successful at getting buy-in from site personnel. They're going to have more resources looking for unusual activity and readily responding and making decisions, and they'll be much more successful in potential upset scenarios than companies that have hundreds of pages of procedures that are copy and pasted from the standard and no one from the site can really understand. From the moderation side, thinking about business continuity plans and resilience strategies that don't focus on preventing the event, but responding when an event occurs to limit the negative impact of that event. And again, those organizations where they can be flexible and operate portions of sites manually, or have fallback plans to still provide partial rates or part of what they're typically producing, will have a much lower overall impact than sites that are completely stuck until a system can be rebuilt. And similarly, thinking about minimizing interconnectivity between separate sites so that there's not a single event that is impacting multiple sites in the production network, to try to limit how bad any single event on an IICS could be for the organization. So those are some ideas of how we can continue to build those concepts out and use them as part of our best practices for security at any of those levels. And so I'd like to end with is just to take that hierarchy of controls and think about moving it from the process safety version to really a security version, where it all starts with identifying, assessing, and understanding the cybersecurity threats for whatever layer we're looking at. Sometimes companies will do a threat model to better understand their component or their system they're developing. Oftentimes, sites will do a cyber risk assessment activity to really understand where their risks lie. And then based on that, we can implement controls in, again, a similar layer of priority, starting with the most effective controls and moving down to the least effective. So if there are steps that we can take to lower the consequence of compromise through inherently safer design principles, by separating systems, by having not having certain aspects connected to the network, designing in such a way that we're not relying on any one system, whatever we can do to lower that consequence is going to have the largest overall impact on our risk equation. From there, once we've done what we can to mitigate consequences, we can look at lowering likelihood with inherently safer design principles. So using mechanical relief devices, using unhackable protections for those certain scenarios that are really high consequence events. Then we could look to lower likelihood through cybersecurity controls to, again, for when we've brought the consequences as low as we can, then using security controls and best practices. And then lastly, relying on administrative controls for that last step of reducing any remaining residual risk. And so by taking this mindset of inherent safety or inherent security or inherently more secure design, we can take an existing framework that has worked well on the process safety side for industrial sites and really take that and use that to guide our decisions around security. And this is something that can benefit, not just operating sites, but also manufacturers and integrators as well, as they think about what steps do they take or what steps are going to have the most improvement on risk with the least impact. And this can really help us to be more effective, more efficient. And really, the earlier in the process that we can stop a potential security threat and prevent it from leading to escalation and a negative impact, the more effective that control will be. So if we prevent a loss of containment event from a control system and compromise of the safety system by using a hardwired relay, that's going to be more effective than providing controls for that safety zone. Or if we have separated control and safety systems, that's going to be more effective than trying to throw all of our eggs into that one combined system basket. And again, depending on the risk for the site, different designs may be appropriate. It's not that there's a single design or that going to a non-hackable protection is always the right decision. But we do need to understand the hazards and risks associated with our specific context. And depending on those levels, pick the controls that are most effective to get us to a tolerable risk position. And so with that, I have just a few slides I'd like to go through. And then we do have some questions, so we'll dig into those for the last 5 to 10 minutes. So if there is interest here, in learning more about the safety aspects, more about the cybersecurity aspects, we do have several upcoming courses, and these are really a great way to learn more if you have some background, but you're interested in getting deeper. The safety side, the FSC 100 course is a 4 full-day course that really goes through the entire safety lifecycle and covers a lot of these core aspects from hazard and risk assessment through SIL verification into operations and maintenance. And then I would also like to just highlight the CS100 course, which is our 4-day cyber course for asset owners that again really looks at a comprehensive approach for analyzing and addressing security risks for the site level. And then in addition to this, we also have a collection of online self-paced training. So if you don't see an open enrollment date that works for you, or you want to get started on your own time and start to dig into more detail, there are a wealth of courses that are offered here that can help to, again, improve understanding and build competency in these areas. And so if you are interested in learning more, please feel free to connect with Exida on social media or to reach out over email or connect on LinkedIn. Always happy to keep the conversation going for those questions that we can't get to in the webinar. Okay. So the first question that we see here is, how do the IEC standards compare to the NIST 853 controls? So there is a lot of overlap between NIST 853 and IEC 62443. I think the first kind of key difference to understand is the 62443 standard is a collection of standards that apply to, let's say, different groups. So there's a subset of the requirements that apply to the manufacturers, a subset that apply to integrators and maintenance service providers, and a subset that apply to the site or the asset owners. So if we think about that slice that applies to the asset owners, the 2-1 part of the standard is the security policies and procedures. So outlines how to set up your security program. And then 3-3 looks at the specific security capabilities for the system. And so between that, there's are some mappings, and there's a lot of overlap between the policy and procedure aspects with some parts of NIST 853 And then from a technical controls perspective, there is some significant overlap in the best practices. I do like the way that 62443 is structured though, because it does kind of help to move from, let's say, having a component that is, let's say, developed in a secure way and then taking advantage of that in the system. So that is one of the benefits I've seen with 62443 to some of the other standards. But certainly the, let's say the concepts of applying security best practices, there is significant overlap between them. Okay, so I'm seeing a couple other questions come in. So one question is, can organizations be certified to IEC 62443-4-1? And so the answer to that is yes, absolutely. There are a number of certification schemes available. exida has some schemes, ISA Secure has schemes for cybersecurity, and so that can be used to evaluate the security development process for manufacturers, and also products or systems can be certified as well if they meet certain security requirements. Okay, so this question here is there any tool available for central asset registers? So yes, there are certainly a number of network monitoring tools and tools that are out there and readily available to start to build that asset register. And if we think about it, having that list of assets is really necessary to look at minimizing your attack surface because you can't control what you don't know that's there. For some sites, if they use active detection, they might use just a simple Nmap scan. Now, again, you want to be careful of the settings you configure because if you go with a heavy or detailed scan, it may create more traffic than you want on the network. Some companies will use passive monitoring like Wireshark to get an understanding of the network assets there. But then also a lot of the larger monitoring solutions also have an option for passive discovery to build that asset inventory. So certainly if that's something that you're interested in learning more about, definitely feel free to reach out, and there's plenty more that we can talk through on the discovery side. Okay, and then the last question here, is the recording going to be available later? So yes, so we will publish the recording of this webinar. Typically, it will take less than a week for that to go online, but that will be available. Alrighty, excellent. And that looks like our last question for today. So thank you everyone very much for your time. If you do have any other questions that we didn't get a chance to address on this webinar, don't hesitate to send them over, but I appreciate everyone's time. Thanks very much.